Okay, dah pukul 10 dah sekarang. Apa ni, Assalamualaikum warahmatullahi wabarakatuh. Very good morning. So far saya nampak ada 12 participants. So I think as we go on, hopefully more and more people will turn up. By the way, this session will last about 40 minutes. After that, Zoom akan cut off. So I'm sending you another link of a Zoom meeting starting at 10:41. So kalau kalau this particular connections got cut off and we have not finished our discussion, please log in into the other meeting particulars yang saya hantar. I just send out.
Okay.
Okay, so let's get started. So today we're going to cover new topics called additive manufacturing. Additive manufacturing. Oh, by the way, if you look at for this particular session, if you look at the ULearn, there'll be a quiz. So please attempt that quiz. Okay. So you need to attempt that quiz. So attempting that quiz will actually register your attendance to this session, right? Okay. So today we're going to cover a new topics on additive manufacturing. And so additive manufacturing is a process that a bit different compared to the rest of the fabrication process. So if you look at the name itself, is additive manufacturing, means that you add something. So if you take a look at the processes that we have discussed so far, for example, electron beam machining, EDM, so on and so forth, you remove materials from the workpiece. So you have a workpiece, and to fabricate an artifact, basically to fabricate a product, what you do is you remove the unwanted portion of the materials. But this process, additive manufacturing process, you start from nothing. So you don't have a workpiece. So you build upon materials that you use for this additive manufacturing to make something. So this is the major difference between additive manufacturing and other manufacturing processes. So outline for this particular topics, we're going to look into introductions, and we're going to discuss the general steps in additive manufacturing. So basically, there are general steps in additive manufacturing. Doesn't matter what techniques you use. In general, the steps are about the same. And we're going to look at additive manufacturing applications, what's being used in additive manufacturing, and we're going to look at the 7 different techniques of additive manufacturing, and then we're going to cover a summary. Okay? So again, if there's any questions, just you can send message to chat, or you can actually just shout out loud. All right. So what is additive manufacturing? So defined by STM, additive manufacturing is the process of joining materials to make an object from 3D CAD data, usually layer upon layer. So that's basically the official definition of additive manufacturing. So it's the joining process of materials. So you have basic materials, you join them together to make an object. And basically, before you can do that, you have to have 3D CAD data, computer design data. So based on that CAD data, then basically you join the materials, and usually the joining of materials is based layer upon layer. So you make a layer at a time. So if you want to make a product, you create a 3D CAD data. And then you cut it cross-sectionally into layers, So what the process will do is it will actually fabricate layer upon layer. So this is similar to, if you guys familiar with medical procedure. They call it, what do you call it? CT scan, or the other procedure is called, I'm not sure what, forgot what's the name procedure. So basically, you can actually scan the internal organ of your body in sections. In sections. So this is also being done for similar procedure in engineering called TEM, tunneling electron microscopy. So it's layer upon layer kind of analysis. So in general, parts are built layer by layer, and typically a typical layer. So there's a typo there. Typical layer. Yeah, typical layer. Thickness is about 0.1 to 0.5 millimeters. So you can actually have a layer as thin as 0.1 millimeters. So that actually will reflect the amount, the kind of accuracy that you can get using this particular process. Okay, let me just quickly. Okay. So the main difference between various process is method in producing individual layer. So as I mentioned just now, we're going to look, there are many types of additive manufacturing. We're going to look at about 7 processes, 7 different techniques in additive manufacturing. And the main difference between the processes is method in producing individual layer. So how do you produce individual layer might differ from techniques to techniques. So this is the main difference between the various process in additive manufacturing processes. So basically, there are general steps in additive manufacturing. The first thing that if you want to manufacture something using this particular techniques, the first thing that you need is you need to have 3-dimensional 3D descriptions of part in CAD file. So you have to use CAD and you have to design 3D representations of the artifact that you want to make. So that's what I showed here. So you need to do this. You can use AutoCAD software, CATIA, so on and so forth. Doesn't matter. So once this is done, then basically the part is divided into slices. Each slice is analyzed and set of instruction is compiled to provide additive manufacturing instructions to fabricate the slice. So once this CAD file is ready, 3D CAD file is ready, then basically you have to slice it horizontally so that you have a layer upon layer. So each of these layer represent one cross sections of these particular parts. So during the AM process itself, then basically each layer will be produced independently. So you make one layer. Once that layer is completed, then only then, or maybe there's a curing process taking place. Once that's done, then basically next layer will be generated. So basically there'll be a fusion of materials from the subsequent layers. And once all the layers are manufactured, then basically you're going to have a product. And again, as we mentioned just now, each slice can have up to 0.1 millimeter in terms of thickness. So you can have a very fine product, surface finish product using these particular techniques. Once you're done with the layer, then you have to plan for support materials. So if you look at this particular product, you have overhang, right? So this product sit on the base, but the subsequent product might not be might be sitting on the air. So because of that, you have to define this support, where you want to have a support for this particular model. So you have to plan for the support materials. Usually, the materials you fabricate for this particular support is the same material that you use for the parts. The only difference is basically the density of the support materials, support structure will be much less compared to density of the actual product. So you manufacture you create your 3D CAD 3D CAD. Once done with that, then basically you section it. Once you section it, you know how each individual layer will be manufactured, and you're going to see some overhang parts. So for the overhang parts, then basically you need to define a support structure. And basically the support structure is using the same material as the product itself. The only thing is the density is going to be less compared to the product itself. And next step is a set of tool direction is determined to manufacture this slice, also shown in the extruder part of section AA from C for the fuse deposition modeling operation. So if you look at this, right, this is the slice of this particular section. So if you slice this particular section, this is what you see. So when the process manufactured this particular slice, then from the top view, what you will see is this. Underneath it, you have something. You have a different slice, right? And you might need to have support materials which designated by different color in here to be fabricated at the same layer. So basically this is a representation of one of the cross sections of the product. Any questions up to here? Okay, I'll continue. So basically that is the general step in additive manufacturing. First, you need to have a three-dimensional description in CAD system. So you have to create the parts in CAD. Once that's done, then basically you have to slice the parts, the product, depending on the thickness of the layer that you want to make. And the finer the thickness, the better the surface finish going to be. Then once that's done, then you have to plan for the support materials where you want to put the support on that particular part. Once that's done, then basically that particular process, the additive manufacturing process, will fabricate that parts layer by layer. And this is the cross-sectional image of that particular section. So if you look at A8, so this is a cross-sectional image of that particular parts. Right? Okay, applications of additive manufacturing worldwide. So if you look at this, then this is basically where AM is being used. This is old data, 2011. If you look at it, majority of it is actually done in the fit and assembly and also direct part production. So this particular techniques back in 2011 is being used in productions to make actual parts. Some of it is done for the prototyping, research, visual aids, so on and so forth. If you read, I think the news, the past 1 or 2 weeks news, UTM actually involved in fabricating face shield for the hospitals for this coronavirus pandemic. So the staff at UTM, and some of it coming from FKP themselves, actually they use these particular techniques to fabricate that parts, additive manufacturing. Examples of applications of additive manufacturing, you have a consumer product. So you can see this. This is basically a basket tray. This is like a seat decorative scene. So this is casing for the USB. This is casing for the holder for the headphone. So you're talking about, you know, consumer parts can be fabricated using this particular process. The only thing, basically, if you look at the economy of scale, if you want to produce in a high volume, maybe AM is not that suitable of application. Yeah. In medical applications, you know, you have object actually being done using 3D printed 3D printing techniques, which is part of additive manufacturing. You can see orthopedic implant. So implant for the orthopedics. So for example, if you want to make a socket for the knee joint, then actually you can use these particular techniques to do it. Or you want to define, let's say, for example, part of the skeleton that's being removed, right? So you want to put some protective surface there using, let's say, for example, titanium or stainless steel. Then you can fabricate that using additive manufacturing techniques. Again, this is, I think this is a joint at your pelvic area. So that's currently is being used and being manufactured using this particular techniques, and implant for the tooth, so on and so forth. Some other applications, you're talking about automobile application. So you have a turbocharger. So this is, for example, if you want to do prototype, then you can do prototyping using metal, aluminum, magnesium, alloy, so on and so forth. Same with aviation. So if you want to have a turbine like this, usually this is done using powdered metallurgy techniques, but you can also use additive manufacturing process to make a turbine like this. Examples of the application. So you're talking about archaeology in here. So replacement for the statue, so on and so forth. So if you want to do a reconstructions on the old statue, then actually you can use AM for that. So this actually indicates the wide range of applications or additive manufacturing. Constructions. So if you look at YouTube, you can actually find a 3D printed building being manufactured, even though it's at lab scale. So it's being done. Arts application, so on and so forth. For sports, you can look. This is basically the shin part, the shin protector, helmet, so on and so forth. So this is body armor. So the application of AM is limitless. This is food applications, and one of the things that that you might heard before. Just imagine if somebody a trip to the space, right? If you want to take a shuttle trip to space in the International Space Station, for example. So so you need some replacement part in that particular station, but to carry spare parts from the Earth to the International Space Center is too expensive because of the weight. So what they do is actually bring one of the 3D printer to the space to the International Space Stations, and use these applications to fabricate spare parts as they need. So rather than bring the finished good of the spare parts over there, they just bring raw materials, so they can manufacture whatever spare parts they need over in the International Space Center. So that's one of the applications that's being used using this AM application. Okay, so for any questions on these topics? No? Okay, a recap. So what we have covered so far is basically we have looked at definitions of additive manufacturing, what it is. The main thing about additive manufacturing is basically the way a product is being fabricated is by adding and fusing materials together rather removing materials. That's the biggest thing. Basically there are general steps in AM process. First, you have to create a 3D CAD data. So once you create a 3D CAD data for the product that you want to fabricate, you have to define the layer, the slicing of the layer of that particular part. And this depends on what kind of finishing you want to have. So it can go down up to 0.1 millimeters. Once you're done with the slicing, then you have to plan for the support system, support structure for your product, for the particular parts to be fabricated. Once that's done, then basically the parts will be fabricated. And we went through some examples of the application of AM, additive manufacturing, just now. Okay. So if there's no questions, then I'm going to move to the first techniques in AM, which is called fuse deposition process, FDP, fuse deposition process. So in fuse deposition process, basically, if you look at the schematic, this is the schematic, this and this, these are the two schematics for it. So basically, what constitute this particular process is it has a gantry robot control movement of extruder head, X and Y direction. So you have a gantry robot. Gantry robot is basically a robot that can move in X and Y directions. So this is basically the head attached to the robotic arms. So it can move in X and Y direction. The table move up and down in Z direction. So the head is attached to the robot and move in X and Y direction, and the table move up and down in Z directions. The extruder head is heated and extrude polymer filament at a constant rate. So basically, there's the raw material for this particular process is basically a filament. Filament of materials, and usually this material is a polymer materials. So the extruder head is heated and extrudes polymer filament at constant rate. So basically, this filament supply is a polymer will be extruded through this particular head, and this head will move in X and Y directions, and this table move in Z direction. So if you remember just now, the process is layer by layer. So what this particular nozzle do is make a layer of sections of the product you want to make. Once that's done, then basically this particular table will move down based on the increment or the slice thickness, and then another layer is fabricated upon that particular layer. So the extruder head is heated and extrudes polymer filament at constant rate. The head follows the predetermined path, and the extruded polymer bonds the previously deposited layer. So basically, the head will follow the predetermined path for that particular layer, and the extruded polymer bonds to the previous deposited layer. So basically, this is what it meant by layer fabrication. When the first layer is completed, the table lowers so that subsequent layer can be superimposed upon the first layer. So that's what happened. So the first layer is done, table Z moved down, another layer is fabricated on top of that particular layer. Right? The fuse deposition process. So part of the overhang sections of the product sections that requires focus. So this is one of the things you have to think about when you create a product like this. So if I want to create a product like this, the first layer that will be fabricated is this layer. right? So I make a dissection of that particular product, that section, so on and so forth, up to this section. Then to make this overhang parts of the product, there's nothing underneath here, right? So I cannot make a layer uh, on top on the air, right? So because of that, then basically I need to have a support system here. So once parts are constructed up to height A, here, next slice would require filament to be placed at the location where no material underneath it. So if I want to make this slice A, right, there's no materials underneath it, so it's impossible for me to do that. So because of that, support material is produced with less dense filament spacing, so that is weaker and can be broken off easily after part is completed. So because of that, then basically I have to make a support structure as shown in this in B, and this is called gusset, right? So rather than this slice, rather than it looks like that, it will looks like that, like this. So as I make this slice, I'll make together with a support structure. So rather than just empty space here, there'll be a support structure here. So there'll be a support structure here. So every layer that I make will have a support structure as shown here. So every time I make a slice, that particular slice, for example, this slice will be inclusive of that particular support structure. Okay? So it looks something like this. It looks something like this with this support structure. That these support structures, because I can control the filament movement to make this particular slice. So from here to here, where you want to make that particular product, the density will be denser compared to the support structure. So that's what it says here. Support material is produced with less dense filament spacing, so that it is weaker. So when you want to make this support structure, so we have 10 minutes to go. Once the sessions end, 10 minutes, please log in into the new session that I sent to you. Okay. Because I don't think we can finish it in time, in 40 minutes. So basically that's what it meant by that. The support material is produced at less dense filament spacing, so that the weaker can be broken off easily after the part is completed. So once the part is completed, you can remove the support structure easily because it's less denser compared to the part itself. So B to E is a common support structure used to additive manufacturing machines. So this is a product like this, right? So if you have a structure, overhang structure like this, you can make a support structure looks like this, right? Similar to this, ceiling with an arc. So if you have a ceiling with an arc like this, right? So you need to have some support structure at the center. So you can build a support structure looks as such, right? Similar to this, so if you have a square support structure, a square roofing like this, you can make the structure underneath it as support structure. So these materials, the support structures, these, and these will be much in terms of density, much denser, less denser compared to the product itself. So once the product is completed, you can break off that particular support structure. Okay. So again, on the fuse deposition process, the layer thickness is determined by the extrusion die diameter. So typically ranges from 0.05 to 0.12. So represent the best achievable tolerance in vertical direction. So for this particular process, just now in general, you're talking about 0.1 to 0.1 minimum, about 0.1 millimeter. But for this particular fuse deposition process, there are some process that can go up down to 0.05 millimeters. And this represent the best achievable tolerance in vertical directions. So in the XY plane, accuracy can be defined as 0.025 millimeters. So this is depends on the accuracy of your motor that's moving the head. Material that can be used, so material used, thermoplastic polymer, ABS or nylon, flat wire metal deposition. So you can actually use flat wire metal for this particular process. So if you want to use this particular process to make a product using metal, you can use it. You can use metal wire. The only thing is you need additional process where you might need to have a laser to hit and bond the deposited layer. So just imagine at the head of the nozzle, at the head of this nozzle, you can have filament of wire, and at the same time next to it you can have a laser. So as it moves, it dispense the materials, and at the same time, the laser behind it will actually cure the materials and fuse them together. Surface of FDM produced parts will indicate a step surface in the oblique plates. So whenever you see this particular FDM process, the surface finish, you'll see this step surface, right? Because it's being fabricated layer by layer. So because of that, basically you're going to have that layered surface. So in order for you to remove or lessen the effect of the step surface, you can do secondary operations, finishing operations of that particular part, using a heated tool, sanding, polishing, or coating to smoothen the surface. So this is the examples between before and after media blasting. So this is as finish finish process using FDM process. So you can see the step surface. So you can lessen the effect of the step process by using media blasting, so sand blasting or media blasting process. So once you blast the surface with media or sand, basically you're going to smoothen the surface and get rid of that step surface finish. Advantage of FDM process is quiet, non-toxic, and office-friendly process. Fast for small, thin shapes, produce strong parts, cost-effective, so on and so forth. Disadvantages of this FDM process is slow when making large cross-sectional areas. So this process is basically relatively slow if you are talking about a large cross-sectional area. The other disadvantages is basically you need to use additional support materials if you have overhang product. Relatively low accuracy and poor surface finish. This is compared to, say, for example, other process like grinding process or CNC machining process. You can achieve a more accurate product compared to this particular FDM process. Unable to make complicated parts. So because of the fabrication is done section by section, layer by layer, sometimes it's very hard for you to make a complicated parts without having overhang. Limited number of materials available, so not that many materials that you can use for this particular to make parts using this particular process. So these are some of the advantages and disadvantages of FDM process. Any questions so far? So what I'm going to do, basically, these particular topics need to be covered in two sessions. We can cover in 2 sessions. So what I plan to do is to take question and answer from now onwards until the end of 10:40, and then we stop there. There are videos that I want you to watch in the ULearn, from the ULearn. So look at the video on your own, and also please please attempt the quiz after this, right? So I think we are not going to continue for the second session that I just set up. I think hopefully I can answer a few questions for the next 2 minutes. So any questions? Any questions? Yes, Wani. Wani Zawani, you have questions? You can either type your message here, or you can ask question directly. Okay. Okay. Questions about the assignment. So what's the question on the assignment? Okay, what's attribute? So attribute is basically the sifat. You know, attribute is sifat of that particular process. Attribute is sifat, you know, is characteristic. So that's what attribute is. Did I answer your questions? Any other questions?